Hi, in this mini lecture I will present two examples of sequential systems that process the multi-bit numbers in series. Let's start with the first, which will be a 2's complement generator. You know this from combinational system part of the lecture, and as you remember, the 1-bit cell of this 2's complement generator has 2 inputs and 2 outputs. The given bit of the input number and the corresponding result bit, and the PI input information coming from the lower bits and output of the same information. And the cell should know about if there was at least a single one in the lower part of the number, okay, to work properly, to properly send or process the input into the output bit. As you remember, if the two operations are possible or are needed here, the first cell starts with copying bits until the first one occurs, including this first one, and then invert the remaining bits until the most significant one. And in the case of sequential system, the block diagram of the cell will be very similar, having an AI, and this input will on this input you will put the consecutive bits. All the bits will be present here, and they will be present from the least significant bit, and on each clock signal you will put another one, the consecutive one, and a single out YI. What about PI and PI plus 1? They are not present here, and this information, of course, is very crucial, but will be stored internally as a state signal P. In general P, because it is a single cell. So you put the multi-bit number starting from the A0, A1, etc., n minus 1, and the length is not defined, can be that the A can be of any length, and the same is true for Y. You will get Y0 first, then Y1, etc., Yn minus 1 as a result of 2's complement. Yeah. And how to start with? And we must think about the signal P as a state signal, and you know that the P can have only two. It is enough to have only two states. The first state will be associated with copying. So copying is the first state. We start with this just after a reset. So the reset is also needed to have it first, after, yeah, at the beginning, if you'd like to start the operation. A reset is needed. And the second state is an invert state. Let's do this in the convention of Mealy machine. You've got the states only inside the circles, and the output signal Y will be presented aside of arrows. When you move from copy to invert, when there is the first one, yeah, switches to the state, and there is no return. There's no return arrow. Again, back to copy state. So what you do if you've got this first one? What about output? this first one should be also copied, okay? But before you've got this first one, you can have zeros. What about zeros? Zeros should also be copied. It is a slash y. Okay, I, doesn't matter. And that's all about the copy. You've got the next state defined for A0 and for A1, okay? And after the first one, you must stay until the infinity, until the end of the number, the input number. You must state and invert the bits. So if you've got A equals 0, you must produce 1. If you've got A equal to 1, you must produce 0. And it is now fully defined state transition diagram. So we can start designing it. Let's suppose you've got the SR flip-flop. It is enough to have a single one because you've got only 2 states. And the state transition, the design table is the following. You've got AI here, let's call it A, and then the state. The state you must associate with the SR flip-flop, which has a Q of T as a state. It is this signal P, sorry, and the Q of T plus 1 is the next state of P. Yeah, the next value of the state vector. In this case, it is similar as P in the case of a combinational version, and Y is the output function. Then you must have S and R as the inputs of the state flip-flop. 0, 0, 0, 1, 1, 0, 1, 1, all the cases are here. And you simply read out the next value and Y from this diagram. So in the first row, you are in state 0. Let's assume that this will be 0 and this one will be 1. Okay, so after reset, you are in state 0, which is shown here, and you've got A equal to 0. Okay, so you've got this arrow, you go to the same state. The same state is here, so 0, and Y is equal 0. Okay, so Y is read from this bit. In the second, you are in invert state, and you've got 0. You've got 0 here, so you read Y, and you stay in the same state 1. Next row, it is this one, you are again in copy, but you've got 1 on the input, you get Y, 1 on a Y, and you go to invert. And the last arrow is you are in invert here, and you've got 1 on A, you get 0 on Y, and you stay in the same state. And what about SR? As you I hope remember, if you've got this change from 0 to 0, you have 2 options: don't change, 0, 0, or reset, 0, 1. So you summarize it using don't care states here. And 1, 1, you've got also 2 possibilities: don't change anything or set. So don't care 0. 0, 1, only 1 possibility to setting the flip-flop. 1, 0, set. And the same as in the second row, don't care 0. Now your task is to find the equation for S and the simplified equations for S and R. Let's scan it. It is the same as A. Okay, if you substitute here 0 and here 1, and R is equal to 0 if you substitute 0. So very simple functions. Let's wipe out. This table is no longer needed. No, it is, sorry. The Y is also important. It is a simple XOR of A and Q of T. And now you can wipe out everything which is in the table. Okay, and now we are to draw the diagram. The logic diagram is the following. You've got the SR, flip-flop clock is here, Q is here, and A is here. You must connect your input to a S input of the flip-flop. To R you must put 0, ground signal, and here you've got an X or gate and Y. That's the same. And reset, okay? So we must also put a reset asynchronous, let's say reset to this. Yeah, because there are versions of SR with reset, asynchronous reset. So from point of view of user, you've got a single input, single output, and clock. It corresponds to this. Okay. Let's switch to another example, and we will derive a comparator, and a series comparator, or iterated in time. Yes, it is another name for these devices which process the signals serially, as an iterated in time, iterative circuit which iterates in time. And you've got what? And you've got the A0, A1, etc., B0, B1, etc. There are two numbers in binary codes which are to be compared, greater, equal, lower, and the P and Q output of the overall result. Let's encode this P and Q similarly as in the case of combinational systems. And this, let's say it is A equal to B, it is A greater to B, it is A lower to B, and not used. So CK is here. So you put the number starting from the lowest bits. You can reverse the order. You know that the comparator can be built in the other direction as well. And what about the states? Let's do it as a Moore machine. Moore machine. So we start with the initial state, which is let's say the equality state. Let's name it S1. When there is 0, 0, you start with this signal after reset. Then, if you've got the same bits of A and B, so 0, 0 or 0 or 1, 1, you stay in the same, in this state, okay? Because they're still the same, after putting the consecutive bit. But if you've got the differences, 0, 1 or 1, 0, of course, A is first, B is the second, you must switch to another states, showing on the output that in this case B is higher because it is 1 on B, B is higher 1, 0. And in this case B is lower as 3, 0, 1. Okay, 0, 1. And again, if the next bits are the same, 0, 0, 1, 1, you stay in the same states, 0, 0, 1, 1. What about if you've got 0, 1 here and 1, 0 here? Because the direction is from the lower to higher. So the next bits are higher, so you must change your decision. So you go here and you go here. If you've got 0, 1, I will wipe it out and put on the left hand side 0, 1 here and 1, 0 here. So you must change. You have now fully defined the state transition diagram, as I can see, for all 4 possible states on the input. 0, 0, yes, and 1, 1. Okay, so 0, 1, you stay in this, and for 1, 0, you stay in this. 1, 2, 3, 4, 5, 1, 2, 3, 4. Okay, 1, 2, 3, 4, 1, 2, 3. That's right. And of course, as you remember, there is one unused state. It is not